the applications from 3D facial reconstruction is for face recognition, animation for movies and video games, and face surgery in medicine. And so what are the challenges that we have to face when we want to build the 3D reconstruction of the human face? So the method must be comfortable for the subject. For example, when we use the fringe pattern to build the 3D reconstruction, it might, cause uncomfortability to the subject. And some people have to use speckle pattern to paint on their face. That'll be really uncomfortable. And another difficulty we have to face is the face has no natural texture except the pores, and which are very small to see. And human faces have similar structures. We all have two eyes, one nose, one mouth, and only the small features can make our human face different. And the technique must be very accurate to detect the different human faces. And so the previous techniques that other people have done have many limitations. One of them is they need to have a lot of cameras. The reason is because the pores on our skin are very small. We need to have many cameras. Each camera will cover a small part of our face so that we can increase the resolution in the image. And another limitation is their results has a low resolution, means they cannot detect the small changes on our facial expression. And another limitation is the long processing time. Some techniques takes hours or even a day to complete building the facial, the 3D face. And some techniques use a template model, means you have a facial template model, and then you just need to change some parameters, features in there, so that the model will become similar to the face you want to build. And in this technique, of course, it is not accurate because it depends on the number of parameters you used. So you'll see here, this is the very famous system from Derek Bradley, University of British Columbia, and he's published in SIGGRAPH 2010. He used 14 cameras, means 7 pairs of cameras, with the LED to increase the lighting on the human face so that you have the best focus on the image. And this is, of course, it's very expensive. And here is a very well-known technique of Furukawa from University of Washington. He used a painted speckle pattern to do the DIC. They don't call it DIC, but similar to DIC. In computer vision, they call image matching or image alignment, and together with the camera calibration, they get the 3D reconstruction of the face. And this is the another famous technique of Bernd Bickel. And you see, in these techniques, the limitations of using a lot of cameras cause the system to be very expensive and sometimes unaffordable, and sometimes it's unportable. You want to build a system that is easy to use, easy to set up, and these are really complex to set up. This will cause cause the subject to feel uncomfortable because every time you have to paint your face and then you want to wash them after doing the reconstruction. Here is the example of having a low resolution results. As you can see that the face here do not have much details. Here is too rough. And these are the limitations of previous techniques. So in our lab, we present a simple system using only 2 cameras. These 2 cameras has a resolution 2048 times 1024. So it's very kind of say financial efficient because it has a much lower resolution than previous techniques. And we only use 2 cameras. Other people have to use a lot of cameras. We only use 2 cameras. So you will be surprised how we can get a good result with such a simple system. So I'm going to explain the algorithm we have used for this system. So in our system, I try to minimize the angle between the 2 cameras. The reason is our nose will cause the occlusion between the 2 cameras. So we want to minimize the 2 angles. But it has to have a minimum angle. Otherwise, if you have 2 small angles, the reconstruction might not be good enough. So another thing is you have a low-cost camera, so you want to maximize the efficiencies of that camera. So I want to capture in such a way that your face is perfectly into the camera, so that you get the best resolution. And a thing that everybody knows is you have to tune it to best focus. But I want to emphasize it here because it's really important. When you tune your focus, sometimes you think it's good enough, but maybe it's not the best one. So we have to use small text, really small text to tune the best focus we can. So the focus is really important because you're using a low-cost camera with low resolution. So you want to maximize the efficiency of your cameras. And so lighting, as you can see in Derek Bradley's paper, they use a LED system, which is expensive. But here we only capture in a normal light room condition. So you can use the additional light to have a better focus by reducing the aperture. So if you have a smaller aperture, your image will be darker, but it will have a better focus. So in this technique, we will be used to build the 3D face. Mainly, we use the digital image correlation. So we find matches between 2 images, and based with the camera information, the matches will give you the 3D coordinate at every point on our face. So I assume everyone here already know about the DIC, so just briefly skim through it. So we choose a subset around each pixel in the reference image, and then we assume that there's a transformation equation in that subset. Follow this. So we assume every pixel in the subset around the pixel we want to find the correspondence to be, follow that equation. And if F is the pixel intensity in the reference image, and G is the pixel intensity in the target image, then this will represent the difference of lighting pixel intensity between the 2 images. We introduce A and B. This is the lighting scale and lighting offset, so that our algorithm will be, invariant to the lighting. So we want to solve the 6 parameters in the previous slide together with these 2 to minimize this correlation coefficient. And we're solving that by letting the gradient equal to 0. So it's a simple mathematical problem. But then because this one, we use the Newton-Raphson iterative algorithm to find the solution for the above equation. So after applying the DIC, well, after setting the system the best I can and apply the DIC, this is the result I got. So as you can see, there's some part missing. This will be caused by the first reason is if you see that the missing parts mostly lie on the boundary of the face, the reason is those regions are dark, and also they have big stains. As you can see that if this region right here, it'll become smaller on the target image. So it's hard to find those regions there because I applied a criteria that when you have a difference in the stains, then I will stop there so that I don't have to draw the boundary so that the DIC will only run on the face. So it will not run on other regions. The reason that I did that is because when the DIC, if we don't put the control on the DIC, it will run on other regions, and there are some unmatchable regions. It will stop there because to solve the DIC, we do the iterative algorithm. If it cannot find a solution, it just keep iterating, and so the algorithm will be stuck there. So then I found that SIF can be helped because SIF is a technique proposed by David Lowe in 2004, a professor in British of Columbia, and it finds the feature points by using the Laplacian Gaussian. For the details of this technique, you can search this paper in 2004 in the National Journal of Computer Vision, and basically it will find features on your face, and then for each feature it will build for it a descriptor, a unique descriptor based on the gradient information of the image. And then this is the result of the SIF if I apply on my image. This is the SIF matching. And from the SIF matching, I want to cooperate with the DIC we have. So I propose this algorithm. So if these green points are the SIF matching, you want to use the DIC to propagate to all other regions of the face. So as we know, right, when we do the DIC, we can do the manual guess by selecting 3 matches. So the same thing with SIF. We have a lot of SIF points. So we just select 3 arbitrary SIF points, and then from there, we can do the DIC analysis. So if these 3 SIF points, we will find the center of gravity of these points. And if I choose this to be the starting point, what's going to be the problem? Sometimes when you do DIC, right, you don't analyze every pixel on the image. You want to save time. So you want to do on the grid scale, say like 5 pixels away. And then if I choose the red one to be my grid, then I don't want to analyze these white points, right? So I want to start somewhere on the red points. So if I find the center of gravity is here, I want to start here. So this is the brown point. And then I want to propagate the results to other pixels. So I will look for the 4 neighbor pixels in the 4 directions. I find the DSC coefficient correlation. which one has the smallest, I will analyze that one. For example, in this one, this purple right here has the smallest correlation coefficient, and I keep looking the 4 neighbor pixels. The brown is already calculated, so I just ignore it. So I look the cyan one. I look for these 3, and if one of these has the smallest correlation coefficient, I just keep looking his other neighbors. So by doing that, by applying the shift, I don't have to do the DSC manual guess. I have automatic guess, okay? And I can cover some of the regions that I didn't get before. So this is the results when you apply shift for automatic guess into the DIC. So, but that is not enough. That is not enough. So the result that I previously showed you at first result is the one that I try to optimize the DSC analysis by running with multiple subsets, like from 21, 31, 41, 51, with multiple calculation step size. And I found that 31 is the best subset size. But that is not enough. If I use only one single subset, that is not enough. The reason is when you do small subset size, it is very sensitive to noise because the subset is not big enough. But if you do with bigger subset size, the problem is the calculation time will be very long. So we proposed the method that for every pixel on the grid, we analyze with multiple subset sizes, 21, 41, 61, and for each of that with the calculation step size of 2, 3, 4. These are the step size of the pixel inside the subset. For example, if you have like 21 times 21 subset, you don't want to calculate 21 times 21 pixel in there. So you can do with the steps calculation step size of 2 to save the time. So here's the final results. If I apply the shift for DIC automatic guess and multi-subset DIC. So here's the results I got, and pretty impressive compared to other papers, because our paper only used 2 cameras and the processing time is only from 5 to 10 minutes. And you don't have to have a complex setup in a room with LED, with expensive facilities. You only need to have 2 normal cameras in a lighting room condition, and this is the results that we get. Thank you for listening.
This talk is open for questions.
In what sense does your algorithm, for instance, differs from the traditionally doing computer vision? You have apps now even on the market where you can take several images, and in 1 minute you immediately have completely your face reconstructed.
Excuse me, what's your question?
I think this is DIC is more useful to measure displacement and strains. What is the accuracy that you want to achieve in this? In what sense does it differ from traditional approaches in computer vision, where you can do your face reconstruction in 1 minute with a simple app?
Yes, actually, I'm not saying this is the best technique to build the 3D face, and I have just figured out that DIC is usable for building the face reconstruction. Okay, but actually we're thinking about, we're about to do it with computer vision approach, which they would do image alignment in really a fast way, and that will involve the image rectification and also image alignment, but we will do that later. But I will just present an application from DIC into this computer vision field. It seems to me that the computer vision approach will be faster, and they didn't say any about the accuracy, but they just showed the results, and we see that the results from DSC technique is no worse than the computer vision guys. So, but I think that approaching this from the DIC has many limitations. One of them is the speed. The computer vision guys will be faster. So, but apparently, later on in the future, I will do this with the image rectification and image alignment in the computer vision guide techniques. On the Middlebury Stereo Vision website, they have better image alignment techniques, and with that one, they have some kind of requirement, like the images you capture must be rectified first, or something like that. With this one, you don't need to rectify. Yeah.
Are you happy with the answer? More or less. So, you think that the commercial one, the scanning, you know this?
Yeah, I know the scanning.
The scanning.
Yes.
Right. Is faster?
Yes, of course, the scanning will be faster. Some of them use optical flows, some of them use image alignment, and that'll be faster. But in terms of accuracy, I think the DSC will be more accurate, even though I have to do the accuracy test on this, but I have used the same system using the block bore gauge to measure the distance between from the camera to the specimen, and the error is really small. I have read a lot of computer vision papers who work on facial reconstruction. Some of them, most of them, didn't give the accuracy results. I don't know why, but maybe the accuracy is not good enough. Another reason is it's hard. It's hard to measure the accuracy of the face. So I believe that DSC will have more accurate result. That is the accuracy, right? Now I'm talking about the precision. When we do the camera calibration for the system, the error between many times is small, which doesn't mean it's accurate, but it means it's precise. So like the result you get every time is mostly the same, similar. So that means it's really precise.
Okay, let's begin the
Nó có
Now I would like to.
giải thích đéo